In our previous discussions about capacitors, we had assumed the conditions of static equilibrium, that all of the charges had settled into their final positions. It turns out, however, that it takes some time for a capacitor to charge to its fully charged state with charge Q equals C times V, or to discharge from this state so that there is zero net charge on the plates. This time-dependent behavior is called transient behavior. Many electric circuits contain both resistors and capacitors. Here we show a simple circuit containing a resistor and a capacitor, and the circuit is called an RC circuit. The capacitor is drawn much larger than normal for illustration purposes. The circuit also contains a battery and a switch. The capacitor starts with zero net charge on its plates, and then we close the switch. Current begins to flow from the positive terminal of the battery. As positive charges approach and accumulate on the left plate, others leave the right plate and leave a net negative charge on the right plate equal in magnitude to the charge on the left plate. Eventually, the current stops flowing and the maximum charge, Q0, forms on the plates. If we start over and monitor the charging of the capacitor as a function of time, we see the following behavior. The charge accumulation starts quickly and then gradually slows down as it approaches its maximum value. We know the mathematical form of this charging curve and find that the magnitude of the charge on the plates at time t is Q equals Q0 times 1 minus e to the negative t divided by RC, where RC is the time constant in seconds. You can see that the units for RC is seconds in two ways. First, since the exponent t divided by RC must be dimensionless, the units of t and RC must be the same. Second, you can work out the basic units of farads times ohms to get seconds. Now, since e, which is the mathematical constant that is the base of the natural logarithm, is equal to 2.718, after one time constant, t equal RC, the capacitor has a charge Q equals Q0 times 1 minus e to the negative 1, which equals 0.632 times Q0, or about 63% of its maximum charge, Q0. Now, let's suppose that the capacitor is fully charged. If we open the circuit, it remains charged, and we can remove the battery from the circuit and replace it by a wire. If we then close the switch, all of the charge on the positive plate will want to move to the negative plate, and the capacitor will discharge. Again, we know the mathematical form of this discharging process, and the magnitude of the charge on the plates at any time t is given by Q equals Q0 e to the negative t divided by RC, where RC is again the time constant. With E equal to 2.718, after one time constant, the capacitor has a charge of Q equals Q times e to the negative 1, which equals 0.368 times Q0. It therefore loses about 63% of its charge after one time constant. In summary, in this section we have discussed the time-dependent or transient behavior of RC circuits. We have found that the charge Q at time t on the plates of a capacitor in a charging RC circuit is given by Q equals Q0 times 1 minus e to the negative t divided by RC, where RC is the time constant of the circuit. The charge Q at time t on the plates of a capacitor in a discharging RC circuit is given by Q equals Q0 e to the negative t divided by RC, where again, RC is the time constant of the circuit.